Sarah, can I give you the mic? I don't know. If you can put it on. I don't know exactly how you want to.
Okay.
How you
Oh, here.
if you have any.
There we go.
So, good morning. Good morning. I would like to welcome you here again. Today we start the second part of our guest lecture series. Last week we talked about Bayesian inference in general and then approximate methods used for Bayesian inference. And we were mostly focusing on parametric models. This week we should look at non-parametric models, including Gaussian processes and Dirichlet processes. We will also look at sampling methods in Bayesian inference. Okay, thank you. Good morning.
Thanks. Okay, so today I will talk about Bayesian regression and Gaussian processes. I'll mostly focus on Bayesian regression today and introduce the notion of Gaussian processes. Okay, let's start off with some references. What I'll be presenting today is mostly a summary of the lecture notes of Carl Rasmussen and Zubin Ghermani's course on machine learning. And they have about 5 or 6 lectures dedicated to Bayesian regression and Gaussian processes. So if you want more details, check out their lecture notes. All their course materials are available at this website here. And if you want even more detailed information, you can go to Carl's book, Gaussian Processes for Machine Learning. And this book is freely available on the web if you want to check it out. And I should also say that most of the figures are taken from these lecture notes, which in turn are taken from this book. So the question we want to answer today is, how do we fit this data set? We're given some input, x, and we have some output, y, and what we want to answer is, if we have a new input value x, how do we predict the value of y? So our input data will denote as x. In general, it can take values in some space script x, and the output in general can take values in some space script y. So y may be continuous, and then we call this a regression problem, or if it's discrete, we call it a classification problem. So today we'll just be focusing on the continuous case when it's a regression problem. And as I said before, our goal is to predict y for a new input value x star, given our training data. So we need to define some model to model the behavior of y given x. We assume that there's some input-output mapping, f, which maps our input space to our output space. And this mapping is contaminated by noise. So that means that what we actually observe is a noisy observation around this input-output mapping. And we'll further assume that these errors are IID normal with some variance sigma squared. So now we need to make some assumptions on our mapping. So classical approaches restrict f to lie in some class of functions. This can be done by representing f as a linear combination of basis functions, phi, with some weights w. So one example is if I take phi m of x to be equal to x to the power of m, and this means that we're restricting f to lie in the class of polynomial functions. So in this setting, our model parameters, the things that we're interested in estimating or making inference on, is the vector of weights. And the structure of the model is defined by m, the number of basis functions, and our basis functions ourselves. So some models in in Bayesian inference actually consider M and say some parameters of phi to be also parameters of the model that we're interested in estimating. But for now, we'll consider that these are fixed, decided by the researcher. So here's some examples of polynomials as M, the number of basis functions, and the weights vary. So here, obviously, if we just have M equal to 0, we just have horizontal lines, M equal to 1, more flexible lines, and so on. We get more and more flexible functions. For a given M, we might have some prior belief on how the function looks like, so what types of weights we believe are probable. And this can be expressed through our prior. So a classical choice for the prior is the normal distribution. And this is chosen because, as we'll see, it has nice computational properties. But it's also chosen because the parameters are easy to elicit. So the parameters are just mu0, which we can interpret as our prior guess of what we think the function will look like, and the parameter sigma 0, which we can interpret as the variability around our prior guess. Or we can also specify sigma 0 by the range of what we expect, of functions that we expect to see. So how do we sample from our prior? So we first have to specify our basis functions, our number of basis functions, and we have to define our prior parameters mu and sigma naught. Then we just define a grid of x values. We compute our basis functions for each x in the grid. We sample our weights, and then we can compute our function. So here's some examples of samples from the prior with polynomial, restricting f to lie in the class of polynomials of maximum degree 17. So this is always a good practice to do when working in Bayesian inference, seeing what prior samples from your functions look like. So now the posterior. A rough idea of what the posterior does is you can consider that we have many different prior samples, and we're just throwing away the samples which don't fit our data, where the fit of the data is measured by the likelihood. More formally, the posterior adjusts the prior density by the likelihood term, which again measures the closeness between the data and the function defined by our weights. So notice here that as opposed to maximum likelihood, we don't just pick a single weight, but we have many, and they are weighted by their posterior probabilities. So this posterior can be easily computed if we assume the Gaussian likelihood, and if we assume the prior on W is Gaussian, then the posterior is Gaussian with updated parameters. So the updated variance, or the updated precision, the precision is just the inverse of the variance. So if we take the inverse here, it's just the prior variance plus some positive term, which depends on our feature space. And the weight, our updated weight, we can view this as it's just a mixture of two terms, right? The first term is our prior guess on the weights, and the second, and the second term, we can see this as our maximum likelihood estimate. If we just write phi transpose phi, phi transpose phi inverse here, we have the maximum likelihood estimate weighted by the precision of the maximum likelihood estimate. So we have a mixture of the prior guess and our maximum likelihood estimate. So here phi, this is the n by m matrix where the ith row is the basis functions evaluated at the ith input value. So here, note that the Gaussian prior is the conjugate prior. So if you're not familiar with the idea of conjugacy, this just means that the posterior maintains the same form as the prior, just with updated parameters here. So are we all familiar with the idea of conjugacy, pretty much? Okay. So let's just go through how we actually compute the posterior in this case. We saw how to do this, some updating rules with Miguel last week. So I just want to go through how we actually compute this. So we said the posterior, as a function of W, it's just proportional to the prior times the likelihood. So this is the prior. Again, we can ignore the normalizing constants. And here's the likelihood. We can ignore the normalizing constants. Instead of the sum of squares, I write this in matrix notation. We can just expand out this term here. So we have the quadratic term in y. And this factor can go into the normalizing constant since it doesn't depend on w. And then we have a quadratic term in w and the cross term. So we need to keep these two terms here, here, and here. And we can do the same thing with the prior, right? We have this quadratic term in w and the cross term that we need to keep. Then we can just rewrite this here. You notice here that this was our updated precision. And we complete the square, and we get something that looks like a normal distribution with our updated parameters. Okay, so for you to practice doing this, I want you to consider a similar setting. So here's an exercise for you to do just at home. So we take the same model, but we assume now that our variance is unknown. Given our weights and our variance, this are independent, normal, centered at f of xi with variance sigma squared. Now, the conjugate prior in this setting is the normal inverse gamma. So we're going to assume our prior for w and sigma squared is normal inverse gamma with parameters, we'll say mu0, c, a, and b. So this means that, so we specify the joint density by defining the marginal density for sigma squared and the conditional of the weights given sigma squared. So this means that the marginal of sigma squared is an inverse gamma with parameters a and b. So this is the rate parameter. So that means that the density of sigma squared is just beta to the a. It's just the normal gamma. We just have the inverse here. Okay, and then w given sigma squared is normal with mean mu0. And now the variance is c times sigma squared. So this is the conjugate prior in this setting. You can also... Three rows up. Oh, sorry, you couldn't read what that said. Yeah, that's just, you know, some people parameterize the gamma in terms of well, it's the shape, the scale, or the rate. So this was just specifying that. Okay. Okay, so now the exercise, well, one exercise you could do here is actually show that this is the conjugate prior. But the main exercise would be to compute what are the updated parameters. So since this is the conjugate prior, we know that the posterior is normal inverse gamma. Oops. Sorry, this is given the data, of course, since it's the posterior. with updated parameters. We'll call it W hat, C hat, A hat, and B hat. So I'll give you the answer, and you can work it out yourselves what it is. W hat, or let's start with C hat. C hat has a similar form to what we saw before. So it's just our prior precision plus the term involving, a positive term involving the x. W hat, our updated mean, is again C hat, C inverse mu 0. And then we have phi transpose y. A hat is just A plus n over 2, n is our sample size. And B hat is B plus 1/2. We can write this second term in several ways, so I'll write it in two different ways. One is, so this is our y minus phi transpose, or phi times mu naught transpose I n minus phi transpose C hat phi. And then we have this term again, so it's the quadratic here. Okay, another way to write this term here is y transpose y plus mu naught C inverse mu naught transpose minus W hat transpose C hat inverse W hat. Okay. So you can see that we get very similar updates to this setting here. What you see, the differences is those terms that I said just go into the normalizing constant. They collect in this updated parameter B hat. So before, when I was just saying these can go into the normalizing constant, now we have they depend on sigma squared. So they get collected in the updated parameter of B hat. Sure. Sorry, yeah.
That's okay.
Mix the notation a bit. Here, that's all transpose. Okay, I think that's correct now. Okay, so now let's look at the predictive distribution. So if we're given a new value of x, we may be interested in the posterior distribution of f at x star. So this is just the linear combination of our basis functions evaluated at x star, which we can write in this notation here. So from properties of the Gaussian in particular, we know that if x1, x2 are normal with mean mu1, mu2, and variance sigma squared 1, sigma squared 2, and the covariance. Then we just have that any linear combination of them is Gaussian with mean A1 times mu1, A2 times mu2, and then the variance is A1 squared, sigma 1 squared, A2 squared, sigma 2 squared, plus 2 times A1, A2 times the covariance. So that means that this term We can rewrite this just as A transpose mu and A transpose, if we call that sigma. So that means that this f of x star is just normal with mean w hat transpose phi evaluated at x star, and we get this variance term here. So the predictive density of y star of a new y, given the data, is just the prediction evaluated at each w, where this predictive density is weighted with the posterior probabilities. So in our case, this is quite simple. Since y star is just f of x star plus an error, we have the same form here. We just need to add the sigma squared for the extra variance coming from the additive independent error that we add to y star. So in this example here, you can also try to figure out what the predictive distribution of y y star is. And in that case, you'll get a t distribution if you want to try out for that example. Okay, so now how do we summarize the posterior, the predictive? So often we get this, we have the entire posterior distribution of y star, but we may just be interested in a point estimate of y star or some summarizing quantity of the entire posterior distribution. So we summarize this by defining an appropriate loss function and then finding the estimator which minimizes the posterior expected loss, or the Bayesian risk. Posterior expected loss is also known as the Bayesian risk. So here's an example. Suppose that we're interested in obtaining a point estimate of f evaluated at some new value x star. So we need to define a loss function. So this says that if our true value is f star and our estimator is f star hat, what is the loss that we get from using our estimator f star hat when f star is really our true value? So one example we can use is a squared error loss. So it just takes our error in using f star hat as our estimator and squaring the error. So in this case, our point estimator is, again, it's the estimator which minimizes the posterior expected loss. So we can derive out what our estimator is in this case. Here, just add plus or minus the expected value of f star, which we just saw on the previous slide, is this term here. Then we can expand this square. So we have this square term, and the cross product. The cross product disappears because what's random here is f star. F star minus its expected value is just 0. So this term goes away. This term doesn't depend on f star tilde. So we can get rid of that term. And then this is the thing now that we need to minimize, right? And this is just minimized by setting f star tilde equal to this expected value. So we get, under the squared error loss function, that our point estimate is just the posterior mean. So this is, in general, what you get. If you use the squared error loss function, you'll get that your point estimate is the posterior mean. Other examples of types of loss functions you can use is the absolute error loss. And if you derive out what the estimator is in this case, it's the posterior median. Another example is the 0,1 loss function. So this puts a loss of 0 if our estimator is equal to our true value, and a loss of 1 in all other cases. And in this case, our estimator is the posterior mode, which is also known as the map estimate. So if you want to try that, this one is quite easy to prove. If you want to try this one on your own, this one requires a bit more work. So connections with penalized regression. I don't know if people in the room are familiar with penalized regression. But so the map estimate, we said it's the estimator under the 0,1 loss function. So we just find the value of W, which maximizes the posterior density, or the log of the posterior density. And you can see that this looks very familiar to the estimator that you get in penalized regression. So we just have the likelihood term plus some penalization term, which means that our prior just corresponds to the penalization term in penalized regression. So for example, if we use a normal prior, that would be similar to ridge regression. If we use Laplace prior, that would be similar to lasso. So I should say that also in our simple case, since we have a normal distribution, our posterior mean corresponds to our map estimate, but in general, this won't be the case.
Can I ask?
Sure.
The previous slide, why is it called point estimation?
Because we have the entire posterior distribution of, say, f of f star. So it's called a point estimate because we want some summary. We want some point estimate of our entire distribution. Is that okay? Okay, so now we'll move on to Gaussian processes. Okay, so Gaussian processes, these are defined. So before we were restricting f to lie in some class of functions. Now we want to put a prior on f where we don't have to restrict f to lie in a class of functions. We want a general prior on f. And one possible way to do this is by using a Gaussian process prior. So this specifies a prior directly on f. So we consider the same model before, we just use a prior directly on f. A Gaussian process is a generalization of a multivariate Gaussian. So a multivariate Gaussian defines the distribution of a finite set of random variables. A Gaussian process will define a distribution on an infinite collection of random variables. So here's the definition. A Gaussian process is an infinite collection of random variables where any finite number have Gaussian distribution with consistent parameters. So we'll see on the next slide what this last statement means, consistent parameters. So we said before that the Gaussian distribution is fully specified by the mean and covariance matrix. Again, we have that our random variables here are indexed by a finite set. The Gaussian process, instead, is fully specified by a mean function and a symmetric positive definite covariance function, which we'll denote as k. And it assumes that for any, if I take any finite number of x's, then these have Gaussian distribution with mean specified by our mean function and covariance matrix specified by our covariance function here. So now instead of indexed by a finite set, we have indexed by x in some general space. And we'll denote this by just GP. F of x is GP with mean function m and covariance function k. So let's just review some properties of the multivariate. Oh, sure. Sorry? The n? Oh, okay, sorry. So this holds for any x1, xn, and any natural number n. So if I take any, yeah, so this isn't, for example, our sample size here. This says if I take any, so I have a general space x, and I take any finite number of x for any finite number too as well, then I have that this holds here. Is that clear? Yeah, so this should say for any xi in x and any natural number n. Here. Okay, so let's just review two properties of the multivariate Gaussian. The first is the marginalization property. So if I have F1 and F2 are normal, these may be vectors themselves. They're normal with mean mu1, mu2, and this variance-covariance matrix here. Then marginally, Fi is normal with parameters obtained from here. I guess this is a little typo here. This should be sigma squared II to match this notation here. And the second property is the conditional property. So this means that F2 given F1 is also normal, and its mean is linear in F1, and its covariance matrix is given as this term here. So this first property, the marginalization property, will be important in showing that the Gaussian process prior actually exists. So we can actually define some stochastic process with marginals that are Gaussian, as we specified before. Yes? Mm-hmm. Consistent parameters, I meant that it's defined with a mean function and covariance function. So the mean and covariance matrix are defined in this fashion here, from a mean and covariance. Yeah, and then we'll see on the next slide that having this actually does imply that there exists a stochastic process with these marginals. And this conditional property here, this will be important in calculating the posterior of a Gaussian process. So we'll come back to this second property later. So the existence of the Gaussian process relies on the Kolmogorov extension theorem. So I'm not going to go into the details of this, but roughly it says that if I take any vector of x and I define some collection of marginals, so for example, we use our normal distribution as the marginal distribution of f of x1, f of xn for any subset x and any natural number n, then these marginals imply that there exists a stochastic process f of x indexed by x in some general space x if our marginals satisfy two properties. The first is invariance with respect to permutations. So this is easily satisfied by our Gaussian distribution. If I permute the random variables and the subsets, then I have the Gaussian distribution is invariant to permutations. The second property is that it needs to marginalize. So if I look at the marginal distribution of x1 to xn, and I integrate out one of these variables, then I should still have the same marginal distribution that I have defined by the marginal of just x1 to xn minus 1. And this is satisfied by the Gaussian process from this property too. So in summary, we have that such a stochastic process exists because of this Kolmogorov extension property and the marginalization property of the Gaussian distribution. Okay. So how do we sample from a Gaussian process? This is quite similar to what we did before. We just take, well, first we need to define what our covariance kernel is, covariance function is, and our mean function. Then we just specify a grid of our input values. We compute the covariance matrix for x in this grid. So I'm using this notation here to denote the covariance matrix where each element, it's this matrix here. And similarly, m of x denotes the mean function evaluated at each x in our grid. Then we can sample from the Gaussian process, since we know that this is just a multivariate normal. we can use the fact that if in general, let me erase this. In general, if X is, say, a multivariate normal with mean mu and variance sigma, then we have that X minus mu scaled by the inverse of sigma to the power of 1/2. Then this is equal to Z, where these are standard normal. This is a vector of standard normal. So we can use that to simulate. We just take a bunch of standard normal distributions and rescale them and shift them, and then we get our samples f of x. So here's some examples of prior samples with a mean function of 0. And this covariance function is called the squared exponential covariance function. So here we see that, here's various prior samples. We see that, well, the functions on average aren't 0, but if we look at any x and we average the prior samples, we have that the average is 0 there. You also see that if you look at the covariance function, if x prime is equal to x, then the covariance function is just 1. So that means that at any x, the variability is, so these samples are roughly between -2 and 2. Sorry, what? This one? Yeah, so that's just using this property here. So that if I have, so in our case we have f of x is normal with mean mu of x and variance covariance matrix here. So if we subtract out the mean, we obviously have something with mean 0, right? And if we rescale, sorry, I don't know if you can see this. If we rescale by the covariance matrix to the power of -1/2, we get a vector which is where each element are IID, normal, mean 0, variance 1. Oh, that's the Koleski decomposition. So that's this thing here, to the -1/2.
What is the exponent of the
To the -1/2. So yeah, that's just computing the power of the matrix to the power of 1/2. Yep. So basically, we see that if we average these samples together, we have at each point they roughly average to 0, and we see that the paths roughly lie between -2 and 2. Here's an example of data sampled from one of these realizations. We just add some noise around that sample. So let's see. The Gaussian process is the conjugate prior. So that means that if we have our Gaussian likelihood, if we use a 0 mean Gaussian process prior, so that means I set my mean function equal to 0. In general, we don't need to set the mean function equal to 0, but this is commonly what is done. And we specify some variance covariance matrix. Then we have a Gaussian process prior with updated mean function and updated covariance function. So here's the form of the updated mean function and the updated covariance function, and we'll talk about those in a second. And then we see that the predictive distribution is also Gaussian, and it's the same we had before. We just add a sigma squared term here for the error term that we're adding to f of x. So how do we derive this posterior distribution? We note that, so our observed values y, they're just f of x plus an error. So we can figure out what the distribution of our vector y is. That's just a multivariate normal centered at 0 with this variance-covariance matrix. So if we take any new input values, x star, any vector of new input values for some natural number k, and we look at the joint distribution of our output y and the f evaluated at x star, we have a multivariate normal with mean 0 and this variance-covariance matrix. So now we can figure out what the posterior is, f of x given x and y star, just from the conditional property of Gaussians that we saw on the previous slide. So that said, so if you remember, we said that if we have f1, f2, and this is normal with mean mu1, mu2, sigma 1, 1, sigma 2, 2, sigma 1, 2, sigma 2, 1. Then we have the f2 given f1 is normal. I'm just rewriting what was on that previous slide. So the mean is linear in f1. So we said that the intercept here is just mu2 minus sigma 2, 1, sigma 1, 1 inverse mu1. The slope is sigma 2, 1 inverse sigma 1, 1. And the covariance matrix is our previous covariance matrix minus a positive term. So we just plug that in here and we can get the posterior of f of x star. So we have this intercept is 0, right? Because we have 0 means. The slope here is just given by taking these two terms. So let's go back. You see that here we have given y, we have something that is linear in y. So these are these two terms there. And then the covariance matrix is found just by plugging into this formula here. And as we said before, the predictive distribution is also easily found. We just add the error there. Okay, so let's see a little example. So here's an example where we take the mean function equal to 0. Again, we use the squared exponential covariance function, and I have decreased the noise a bit. So here's some data sampled from this model. Here's an example of our prior samples. Again, we said that the samples roughly lie between -2 and 2 here. And on average, they average out to mean 0. Here is our posterior samples given our data. So this is just, again, a Gaussian process. And we see that the variance-covariance bars have shrunken given our data, and that the predictive distribution is very similar. We just increase the covariance bars by our sigma squared term there. So can anybody guess what happens if I look at the, say, the posterior of f of x, or the predictive of y given x, as I have an input value which is further from our observed values of x? So what happens if I try to predict a y out here at, say, x star equal to 100? So what happens to the mean? What happens to our updated mean? For this case, in which we use the squared exponential kernel, notice that this covariance function is just a function of the distance between x and x star. So if I take a new value x out here, it will be, this distance will be very large between any of our observed values. So what happens to the mean here? This thing is large, and what we get is basically that we go back to the prior. So here's our prior sample here, and this term will basically, the variance that we're subtracting off will become 0. So in this case, when we go out here, our error bars will grow and we get back to our mean estimate of 0 on average. Okay, so let's look more carefully at this posterior of the mean. So this is just rewriting again what the updated mean and covariance matrix is. So you notice that the mean is linear in two ways. It's, okay. Let's just say I equal to 1, but it's linear in our output, observed output, y, and it's also linear in terms of the covariance. So if we take the covariance function evaluated at each of our input data xi, we also have that is linear in this term here, which is something that you commonly see in kernel regression. Our posterior variance is the difference of two terms, so it's our prior variance minus this term here, which is a positive term. So we shrink our prior variance with some term that depends on our input data x. Okay, so before we get to this, let's do just a simple exercise. Okay. So let's take the model that we had before. So now let's just assume that we just have our mean is just a linear function of x with variance sigma squared. And further, we'll assume that these weights are IAD standard normal, I equals 0 and 1. Now, if I define f of x equal to this, then what is the distribution of f of x? Any guesses? So the distribution of f of x, if I take any, so we said a linear combination of Gaussians is Gaussian, right? So f of x is Gaussian. Same if I take any finite set of x, I have something which is Gaussian, jointly Gaussian. So now we know that f of x is a Gaussian process. We just have to find out what is the mean and what is the covariance function. So these models that we were looking at before, roughly they're a subset of these Gaussian process models. So in this example, what is the mean? Any? Any guesses here? Yep, exactly. So the mean function is 0. The mean function is just the expected value with respect to w of f of x. So that is just the expected value, w0 plus w1. Expectation of the sum is the sum of the expectations. So we can just pull the expectation inside here. These terms have expectation 0, so that just gives us 0. So we have something with mean 0. Now, what is the covariance function? Any guesses here? So our covariance function, this is just the expected value of f of x times f of x prime. This is just the definition of covariance minus expected value of f of x. Okay, just delete the. Okay, so this we said is 0, right? Right? This is just the mean function. So this term is 0. So now we have to just see what is this. So this, let's rewrite it. In terms of w, we have w0 plus w1 times x, w0 plus w1 times x. So we can expand this term. We have expectation of w0. Yeah, sorry. So expectation of w0 squared is just the variance, right? Because the mean is 0. So expectation of w0 squared. This is just the variance, which we said it's standard normal, plus expectation with respect to w of w1 squared x prime. The variance of w1 is also just 1. So we have x prime plus the cross term, or the cross terms, which will just be 0 since w0 and w1 are independent, right? So if I look at this term times here, I have expectation of w0 times w1, which is 0 since they are not correlated, since they're IID here. So in the end, in this case, we have a covariance function of 1 plus x prime. Okay. So what we've shown is roughly that well, we'll see in the next slide, but any of the Bayesian regression models that we were looking at before that can be where the function can be represented as a linear combination of basis functions, these are actually special cases of Gaussian processes. Okay. We have a little bit of time, so now let's go back to our previous model. We said that f of x is equal to a linear combination of basis functions. For now, we'll assume that these weights have mean 0 and a general variance covariance matrix. You can replace this with a general mean as well, but for simplicity, I'll assume that the mean is 0. So as we said before, if I take any finite subset of x, the joint distribution is a multivariate Gaussian. So that means that f of x is a Gaussian process. We just need to figure out what the mean and the covariance function is. So the mean function, again, in this general case, we have that it's 0, since the expected value of all these weights is 0. And the covariance function, again, we have the same formula we had before. The mean is 0, so that term goes away. And we just have all of these terms here. So the expectation of the sum is the sum of the expectations. We can move the expectation inside. And here we just have, this is the correlation between weights with two different indices. And this is just the m and m prime element of our variance covariance matrix sigma 0. So in general, we get that the covariance function has this form here. So in summary, any finite linear model with Gaussian process prior on the weights corresponds to a Gaussian process prior with mean 0 in this case if the weights are centered at 0 and covariance function defined here. Okay, so now let's consider the connections with infinite linear models. So in this case, first let's consider a finite linear model where I use these basis functions. So basically, I'm placing Gaussian-shaped basis functions uniformly on x. Here, we just consider x is 0, 1. So you can consider say we have the unit interval here. And we place a bunch of Gaussian-shaped basis functions with different weights. So that's our prior. If we use IID normal errors on our weights, and we consider the class of limiting functions, so we rescale our function by 1 over m. And we take the limit as m goes to 0. We get this integral here, where I also take the limit as the limits of integration go to plus or minus infinity. Then I have that f of x is defined as specified here. So these WU is IID normal 0, 1. So this limiting class of functions is a Gaussian process. The mean function is just 0. So we have expectation of this integral here. We can move the expectation inside. This W of u is what is random. It has mean 0. So we just get a mean function of 0. And the covariance function, we see, well, with a little bit of work, you can show that it is just proportional to our squared exponential covariance function. So roughly, you see that Well, again, we can ignore that minus f expected value of f of x times expected value of f of x prime, since the mean function is 0. Since these weights here are IID normal, we don't have to worry about the cross product term. So we just have the expectation of the weights squared, which is 1. And then we get the product of these two terms here. And then you can just rewrite this here a bit. And then we have something which looks like a normal centered at this term here. And then that's how we arrive at that last line there. So this means that a Gaussian process with a squared exponential covariance function is equivalent to a regression model where we place infinitely many Gaussian-shaped basis functions everywhere. So basically, if I take the limit as these, if I take more and more and more finer and finer approximation, then I'm placing Gaussian-shaped basis functions everywhere.